Thanks, Peter, and the other organizers for including me kind of at the last minute in this. It's great to be able to participate. Of course, it's a somber occasion, and I was grateful to be able to contribute my, not only my work, but my thoughts to honor Eric's memory. I'll take a moment just to recall my own history with Eric. I figured out, I guess I knew Eric for 25 years, maybe 24 years, something like that. As far as I can recall, I first met him at a meeting in Warsaw when I was still a student. It was a meeting in honor of Helena Rasiova, and we spent a couple of weeks together at the Banach Center for Mathematics in Warsaw. I think Eric was there for a longer visit for like a special semester dedicated to Rasiova, and I was there for a special meeting on category theory. I think Eric was working on constructive non-standard analysis, something like that. But that's at least what he spoke about, but he was also working at the time on categorical models of type theory. Of course, this is before the papers with Ika, but he was already working on this kind of categorical logic stuff. And so I was there. I think Jaap van Oosten was there. Maybe Karsten Butz was there. And I remember an urbane dinner with Marek Zawodowski. That's the first time I met Marek. And anyway, so that's my earliest memory of Eric. And then over the years, we visited each other back and forth many times. Maybe the next time was at the Mittag-Leffler meeting in 2001. That was a great meeting where Per Martin Löf talked about intentional types and Ika Moerdijk talked about quill and model categories in a cryptic lecture. Everyone wondered, why is he talking about this at a logic meeting? And I think the reason for that came out soon thereafter. Eric was talking about higher dimensional models of intentional type theory. And of course, in the interim, he and Ika had been working on the series of papers on models, categorical models of type theory. And what Eric told me at the time was that the third paper in that series was supposed to be on models of intentional type theory, and the plan was to use higher categories for that. And he had this result about the fact that groupoids is not locally Cartesian closed. And so there was a puzzle about how to get the pi functors for the type theory. And he had this idea of using bigroupoids, and that would be, and he showed that that category is weakly locally Cartesian closed. So that was one possibility for getting the pi functors. So that's certainly related to my topic today. And I think, you know, the whole course of the development of homotopy type theory goes back to those ideas of Ika and Eric and the idea of using higher categories and of course quill model structures to interpret intentional type theory. I'll just mention a few more events. Eric, of course, organized the first hot workshop that was already mentioned. Richard Garner was there, Benno was there. Forgive me if I'm forgetting who else was there. And that was definitely an important event there in Uppsala. And I visited Eric many times in Uppsala and in Stockholm later. And he visited me in Pittsburgh a few times, and we had quite a close interaction for many years. I just want to say a couple of things I especially appreciated about Eric. One was his how should I say, his support for young researchers over the years without getting a lot of credit or making a big deal about it. He hired a whole series of young people, supported their postdocs and PhD theses in a way that was very kind of unselfish, impersonal, just did it because it was the right thing to do. It was enormously influential in the community of type theory and categorical logic in doing that. I think that was a great credit to Eric to be so supportive of all the young researchers, including two of my own students, for which I'm grateful. I valued Eric's friendship very much over the years. I especially appreciated his quiet warmth and his subtle sense of humor. So, okay, now before I get all choked up, I think I'll go on and talk about some mathematics. So I'm talking today about the Frobenius condition. The Frobenius condition, as I'll explain, is instrumental in getting the pi types in a model of type theory. So that's where we're headed. Let's see if I can get a slide to advance here. There we go. Let me recall the notion of a weak factorization system on a category. So we have two classes of maps. We'll call them the left maps and the right maps. Each class is closed under retracts in the arrow category. And we have these two axioms. Every map factors into a left map followed by a right map, kind of like epi followed by mono. And if you have a commutative square with a left map on the left, and you'll see I'm going to draw the left maps with a little tail like that, and a right map on the right, and I'll draw the right maps with a double head like that, then there's a diagonal map here which makes both triangles commute. So those are the two axioms for a weak factorization system, or maybe three axioms, closure under retracts. Okay, the interest in weak factorization systems is twofold. On the one hand, it's one of the main ingredients in the definition of a Quillen model structure. And on the other hand, it's the main ingredient in the model of identity types in homotopy type theory. So I'm sure you've all seen that before. One thing you might not quite remember is that when you do make such a model of the identity types using a weak factorization system, it's important to also have the following condition called the Frobenius property. I think this was first highlighted by Benno, Vandenberg, and Richard Garner in an early paper on the subject, the importance of this Frobenius condition. So we're going to say that a weak factorization system has the Frobenius property if the left maps are stable under pullback along the right maps. Okay. And we'll see in just a minute that having this Frobenius condition is actually equivalent to being able to model not only the identity types, but also pi types in the system. So let's see how that works. So in order to get the pi from the Frobenius, we're going to use the following fact about weak factorization systems on a locally Cartesian closed category. Let's suppose to keep things simple, that our category is locally Cartesian closed. So if we have any map in a locally Cartesian closed category, there's this base change between the slices where the upper star indicates a pullback and then its right adjoint, which is push forward, say, is our dependent product operation. And now the lemma says the upper star preserves the left class of the weak factorization system if and only if the lower star, the right adjoint, preserves the right class of the weak factorization system. And that's a really nice, simple fact, but the proof is simple enough to fit on the half a slide. So let's just look at it and see how it goes. Let's suppose that we have this condition that the left adjoint preserves the left class. And now suppose that we have G here and that's a right map, and we're going to push it forward and see whether the result is again a right map. So here it is, we pushed it forward and we're checking whether it's a right map. And you can tell whether something is a right map if it lifts against all left maps. So that's not one of the axioms, but it follows from the axioms. And so we test it against an arbitrary left map over here. But by adjointness, we can push this right adjoint over to the left. So there it is. And now remember, we assumed that C was a left map and that F upper star preserves left maps. And we assumed that G was a right map. And so we have a diagonal filler by our filling axiom. And now we apply the adjunction again. And that applies now to the diagonal filler. And it gives us a diagonal filler over here on the right. So that's all there is to it. We just flip the adjoints back and forth. But what's pretty cool is the way the adjointness behaves with respect to this diagonal filling condition. Of course, that's only one direction of the if and only if, but you can see the argument is completely symmetric, and you're going to get the other one in a similar way. So in particular, what that tells us is that if we have a weak factorization with the Frobenius property, remember that said left maps are preserved by pullback along right maps, then by that lemma, the right maps are preserved by push forward along the right maps, right? But that's exactly this dependent product operation. We take a right map, we push it forward along a right map, and we have a dependent product. So that's why the interpretation of pi types, which is by dependent products, is equivalent to this Frobenius property. So there are two reasons why we're interested in Frobenius. One is for the pi types, one is for the identity types. I said the Quillen model structure is related to weak factorization systems. Here's exactly how the relationship goes. The definition of a Quillen model structure is as follows. We have three classes of maps now, not two: cofibrations, weak equivalences, and fibrations. Those are just names. And the condition now is that if I look at the cofibrations and those fibrations which are also weak equivalences, then that forms a weak factorization system. And if I look at those cofibrations that are weak equivalences together with the fibrations, that also forms a weak factorization system. So we have two weak factorization systems that are kind of interlocking in this way. Then there's another condition that the weak equivalences have the 3-for-2 property. That means if I have any commutative triangle and any two maps in the triangle are weak equivalences, then so is the third one. So that's it. That's all there is to it for Quillen model structure on a category. Just as a matter of definition, I'm going to call these fibrations that are also weak equivalences the trivial fibrations, and I'll write them like this. And I'm going to call the cofibrations that are also weak equivalences the trivial cofibrations, and I'll write them like that. So that's a Quillen model structure. And now let's see what we know already just from that lemma that simple swapping adjoints lemma. We know that if the cofibrations are stable under pullbacks, then their right class, the trivial fibrations, are stable under push forwards. We also know that if this weak factorization system, this kind of fibration weak factorization system, has a Frobenius property, then the fibrations will have all dependent products. We just said that a minute ago. And we know that if the cofibrations are stable under pullbacks along the fibrations, so given that condition, then we have this Frobenius property if and only if the weak equivalences are stable under pullback along the fibrations. That's kind of by the factorization. You factor this weak equivalence into a trivial cofibration followed by a trivial fibration. The trivial fibrations are stable because they're a right class. The trivial cofibrations are stable by Frobenius, and therefore the weak equivalences are stable by pullback along the right class. That's a condition that the homotopy theorist calls being right proper. So that's a familiar condition from homotopy theory, and it's intimately connected with this interpretation of the pi types in the category. I just want to pull your attention to those facts. And now let's kind of put that to use. Oh, here we are. So in particular, if I have a locally Cartesian closed category with a Quillen model structure, and it satisfies Frobenius, then from a type theoretic point of view, which is our topic of interest today, we're going to model Martin-Löf type theory with sigma, pi, identity types, if we just take the fibrations to be the types. Okay, so here is a kind of model, if you like, of homotopy type theory in, well, groupoids, bigroupoids, infinity groupoids, and so on, just from these simple considerations. It's taken us 10 years or more, 20 years to get here, but finally, with the benefit of 20/20 hindsight, everything kind of falls into place in this simple way. Okay. So where do we get such a Quillen model category? Well, we can go to the homotopy theorists and ask them for one, and they'll give us loads of them. But there are other ways to get them too. And one neat way to get a Quillen model structure is as follows. It's inspired by some work of Thierry Cocon and Andy Pitts and his student Ian Orton. Let's say that we have a topos. A pre-model on a topos consists of the following three ingredients. One is this phi, which is a representable class of monos. I'll say a little bit more about that in a minute. These are supposed to satisfy some conditions, which I'm not going to go into too much detail about, although I'll tell you the conditions on the representable class of monos a little bit more in a minute. Another ingredient is an interval, that is an object with 2 points, which we think of as the end points. That's going to parameterize some homotopies. And then a universe in the kind of Grothendieck or type theoretic sense. The universe in a topos is something that Thomas Streicher can tell you a lot about. And in the meantime, I think we all know something about that. In fact, I think that Peter de Bier is going to tell us something about Eric's work on universes in categories for modeling type theory. So this is kind of some more or less familiar stuff from categorical logic. If we have such a gadget on a topos, we now know that we can use it to construct a Quillen model category. So from these ingredients, we can construct a Quillen model structure. That's work from the last 5 years or so by these people and others. I think maybe Nicola Gambino should be mentioned in here too. Didn't fit on the line. Probably other people contributed too. But there's a nice construction. I'm not going to do the whole thing for you, but I'll tell you a little bit about what these classes are. And then you can look at the literature for the rest. And in particular today, though, what I do want to show you in more detail is that this Quillen model structure that you construct out of this data has the Frobenius property. So in particular, it's right proper. So that's interesting from a homotopy theoretic point of view. But from a type theoretic point of view, it has those nice properties that we mentioned before. It models the pi types and it models the identity types. So that's what our goal is for this talk. So let's get started. What are the cofibrations? Well, the cofibrations are determined by this thing, this representable class of monos. And the way it works is this. Every monomorphism in the topos has a classifying pullback square with the subobject classifier. And now I look at those monos whose classifying map factors through this subobject of the subobject classifier, this phi. And one of my axioms says that the universal subobject actually factors through phi. And therefore, I get a pullback square right here. And therefore, I get a pullback square right here as well. So this, if you will, is the universal cofibration. And every cofibration has a classifying map into this guy and a pullback square like that. So just like the subobject classifier, this is the cofibration classifier, okay? In particular, it follows that the cofibrations are stable under all pullbacks, right? Because they are by definition the pullbacks of this thing. And so they're stable under pullbacks. So that was one of our conditions there that we were interested in that corollary I showed you a minute ago. So we have these cofibrations and they're classified by this gadget. That's what we care about. This gadget is a cofibration classifier. Now, whenever you have a map in a locally Cartesian closed category, any map, it determines a polynomial functor like this. This description of polynomial functors, it's an endofunctor on the category. Maybe I should, there we go. It's an endofunctor on the category. This description of polynomial endofunctors is due to Mordek and Palmgren, right? It's in their paper on W types. I've looked in the literature to try to find an earlier account of polynomial endofunctors, And I don't know where it occurs. I guess probably Andre Joyal has some work in his stuff on combinatorics that does this, but certainly the connection between W types and polynomial endofunctors is due to Mordijk and Palmgren in the paper on W types. Anyway, it's a beautiful subject. It's been studied in the meantime by Andre Joyal, Nicola Gambino, others, Joachim Koch. And the cool thing about this polynomial endofunctor, as I'm going to show you in a minute, is that this thing has a universal property, which is going to be useful. So one thing is, the other condition on phi that I didn't tell you about is the dominance condition. The dominance condition is due to Pino Rosellini in his thesis with Dana Scott. It's a condition, comes out of domain theory, I guess. And it's, synthetic domain theory. Basically, what it does is it forces this polynomial functor to not only be an endofunctor, but to be a monad. And we're going to make use of that. That if we have that dominance condition on phi, which you can write down with a logical formula, which I guess I should have written down here, it forces this associated endofunctor to be a monad. The unit of the monad now turns out is a classifier for partial maps. So this is the universal property that I was hedging about a moment ago. Whenever you have a polynomial like this, it has a universal property. And in this case, the universal property amounts to this. If I have a partial map into X, the domain of which is a cofibration, so that's what I mean by a cofibrant partial map, then I can complete this to a pullback square by a map into X plus. So in that sense, X plus, together with this eta, is a partial map classifier in the old-fashioned sense of elementary topos theory, but not for arbitrary partial maps, but only for cofibrant domain partial maps. The very early days of elementary topos theory had partial map classifiers as one of the main ingredients. And here it is again, but now it has a cofibrant domain in the partial map. This plus you can think of as a kind of lifting monad if you're a computer scientist. That's what that monad is. It's a monad of partial maps. Okay, so what does that mean? Well, in particular, let's look at the algebras for this monad. In fact, we'll just take the algebras for the pointed endofunctor. So that is just retractions of this unit map. And because this is fibered, we can do this in every slice. And I claim, or I assert, that those algebras are going to be a good class of trivial fibrations, namely a right class for a weak factorization system against the cofibrations. And that follows simply from the classifying property of the partial map classifier. Suppose I have a cofibration over X and a commutative square, which is this composite here, and this cofibration over X, then I want to lift here, but by the universal property of A plus, first of all, I can fill in here with the classifying map, and then I can compose with the algebra structure to get my diagonal filler. So if you think a little bit about how that works over X in the slice category, you'll see that having A over X and be an algebra for the plus over X means that A lifts against all cofibrations over X. So the trivial fibrations form a right class for this weak factorization system of cofibrations and trivial fibrations. The factorization axiom, if you're worried about that, That's what follows from the monad multiplication. So we actually use the whole monad structure there. We use that to get the factorization. I think this observation that this thing is in fact a weak factorization system also goes back to Andre Joyal. In fact, he told me last year in Oslo that he mentioned this in his letter to Grothendieck, the famous letter in which he talks about the so-called Joyal model structure. So I guess that goes way back. I learned it from a paper by Richard Garner, I think. Now, C is stable under pullback. And remember, we had this lemma, which tells us that the right class is therefore stable under push forward. So that's a crucial fact. The trivial fibrations of this left weak factorization system are stable under push forwards. Okay, how are we going to fill out our Quillen model structure? Well, we're going to use this cool Leibniz adjunction. It's an adjunction on the slice categories, on the arrow categories, which comes from operating with a fixed arrow in two different ways. On the one hand, push out product, and on the other hand, a pullback Hom. These are a little hard to digest if you're seeing this for the first time. Just take my word for it that there's an operation which allows me to apply the arrow U to any other arrow F from X to Y and come up with a new arrow of this form. And there's another operation which is a right adjoint for fixed U, which is this pullback Hom. And this is a kind of monoidal closed structure on the arrow category. So that adjunction is going to be very useful now. In particular, as we already observed, there's this nice relationship between adjunctions and diagonal filling. So in particular, this adjunction satisfies this condition where this little slash box means has a diagonal filler in the sense that we've already seen. If this push out product lifts against F for any F, then C lifts against the pullback Hom for that F. So I can scoot the U over back and forth like this, kind of like in a Cartesian closed category inside the Hom sets, right? So I have a filling here for the push out product and a filling here for the pullback Hom. And that holds just by adjointness. It's easy to check. In fact, we've already seen an instance of it. So, okay, I'm going to make use of that now in the following way. I'm going to define the fibrations as follows. I say that F is a fibration if its pullback Hom with this arrow is a trivial fibration, where this arrow that I'm using here is, well, I could say one of the endpoints of the interval. Remember, it has two, and then I would have to do this twice with the two endpoints. But I'm going to be a little more efficient here. I'm going to say, take the slice category over I. Then we have a generic point of the interval, just because that's the universal property of slice categories. It puts in points. I use the generic point, and then I take the pullback Hom with that generic point. I could also do this with the two endpoints individually, but this is a slicker way of doing it. Now, if I unwind, so the point is this, I already know what the trivial fibrations are. They're the algebras for the plus monad. I say F is a fibration if delta arrows F is one of those trivial fibrations. That's my definition of fibration. If I unwind this kind of abstract condition explicitly in terms of E rather than the slice of E, I end up with this. Here's my F. Here's the evaluation of X to the I at the endpoint. Oh, sorry, the evaluation, the total evaluation of X to the I. I'm not working with endpoints anymore. I'm saying here's the total evaluation. Here's the total evaluation of Y. And here's this co-unit applied to F of this adjunction product exponential. I fill in the pullback square by this so-called gap map, and that's exactly delta arrows F. the thing I was talking about before. And now F is a fibration by definition if this gap map is a trivial fibration in the previous sense. That's my nice definition of fibrations. It's very easy to work with. In fact, I'm going to work with it in a short time. Now, you may be wondering, hey, what about all that box filling that I've seen before when people talk about fibrations? Well, that follows now from this definition. F is a fibration by definition if this guy is a trivial fibration. Now, we said before, being a trivial fibration means it lifts against all cofibrations. That's this property. So, but then by jointness, it means F itself lifts against all push-out products of a cofibration and that endpoint of the interval. And this condition is saying exactly that we have diagonal fillers for these push-out products. If you analyze what such a push-out product is, sorry, what's B here? A and B are the codomain of C. C is a cofibration going from A to B. I make a push-out product like that. This thing is a kind of open box. It's an abstract open box. If B were a cube, this would be the next higher dimensional cube, and this would be a kind of open box. So this is the open box filling condition that is maybe more familiar as a definition of fibrations. It's like the horn filling condition for simplicial sets. So this condition that I gave you before for fibrations is equivalent to a horn filling type condition. And now I have a weak factorization system with those fibrations. So this is my other weak factorization system from the Quillen model structure that I'm trying to build. So here are just a few comments. I'm going to define what are the trivial cofibrations. Well, I'll just define them by lifting against those fibrations. It's the left lifting class with respect to F. So the orthogonality condition is immediate. I still need the factorization axiom, and for that, I can use Richard Garner's small object argument. Richard's small object argument was an early paper there. It has kind of an inspiration in type theory as well from studying the trivial cofibrations used in the identity type factorization system. Andrew Swan has recently given a nice constructive version of Richard Garner's small object argument based on ideas coming from the theory of W types. He uses something called W types with reductions, I think. So that's a type theorist's version of the small object argument. You can look at Andrew's paper on that. And in fact, I'll mention that these factorization systems that I've now explained to you, these two different ones, are actually algebraic weak factorization systems. I'm not going to go into the details of that, but just to be brief, well, they're associated to a monad. So this thing we know is a monad. And the filling structures, the diagonal filling conditions are actually structures. That is, we have choices of fillers which are coherent with respect to pullbacks. So that's important in the actual theory of developing this Quillen model structure, that those are algebraic factorization systems. Okay, so those are my two factorization systems. Now, unlike the trivial fibrations, like the trivial fibrations, the fibrations that I just defined, they're of course stable under all pullbacks just because they are a right class in a weak factorization system. You get that for free. But now, unlike the trivial fibrations, they're not stable under all push forwards. We didn't get that for free. That was a non-trivial additional condition. It came from the cofibrations being stable under pullback, but the trivial fibrations are by no means stable under pullback. It's easy to give counterexamples. So we don't know that the fibrations are stable under push forwards. And in fact, they're not in general stable under push forwards. However, we do have this theorem, which was our goal that we're going to prove. The fibrations are stable under push forwards along other fibrations. So the fibrations themselves are closed under push forwards. That's the dependent product that we were talking about, the pi type. And of course, that's the kind of dual statement to this Frobenius condition that we were emphasizing in the beginning. The trivial cofibrations are stable under pullbacks along fibrations. So that's our goal now. We've reduced everything to that basic statement. The fibrations are stable under push forwards along other fibrations. So let's show how the proof of that works. So recall that a fibration was by definition a map F such that when I form this gap map, the resulting delta arrows F, the pullback HOM, is a trivial fibration. There's a lot of information in this diagram. I'm going to denote that schematically like this. Here's the evaluation, this evaluation at the endpoint. I'm just going to write it as epsilon. The pullback I'll write as A sub epsilon. That's just the fiber of A over this map epsilon. Here's that gap map. So, and I'll strike it through to mean that it's a trivial fibration. Okay, so this information is presented schematically like this in this diagram. Okay, Peter's squinting. I'm a little worried that he doesn't get it. Is it okay? Yeah, okay, good. So that's a quick and dirty presentation of this map being a fibration. So suppose we've got two fibrations and we want to show that the push forward of this one along this one is again a fibration. Well, because each of these is a fibration, we have the following. This is our schematic presentation of this being a fibration. And then this one being a fibration is just this square here, because this top composite was the evaluation. Now I pull this one back across the evaluation, and then I put in the gap map. And then this one is a trivial fibration because this is a fibration, okay? I've denoted this with a star here for a reason that I'll explain later. I can't denote it B sub epsilon because that would mean this map pulled back along this one, and that's not right. I want to pull it back along the whole evaluation. So that's the star there. Okay, so this is a trivial fibration and this is a trivial fibration, and these are pullbacks. Now I want to push forward and this map along this one. So there it is right there. That's our pi functor. And I want this one to be a fibration. That's what I'm trying to prove, right? So let's recall the definition. That means pull it back along the evaluation, just like I did here. And then put in this evaluation here and take the gap map. So this is the map that is supposed to be a trivial fibration, right? That's the definition of this as a fibration, is that this gadget is a trivial fibration. So that's what I'm trying to prove. I want to show that this pullback HOM is a trivial fibration. Okay, so now I'm going to use this setup, of course, to prove it. And what I'm going to do is this. I have this trivial fibration up here in this triangle. And then I have this map, and I can push this whole triangle forward along this map to get a triangle here over this base. I'm not drawing the whole thing. It would be too messy. It's enough to draw just this one arrow to indicate that this whole thing is over that base. But remember, push forward of a trivial fibration along any map is a trivial fibration. So this push forward here is a trivial fibration over here. Now, in a better possible world, this would be equal to this. But unfortunately, that's not the possible world that we live in. However, we do live in a pretty good one, close enough, namely, this is a retract of this. And that's all we really need to do, is show that this one that we're looking for is a retract of this, because remember, the trivial fibrations are closed under retractions. So I think I'm not going to take the time to give you the details of this. I can give you some of the details if you ask me in the discussion question session, but that's the basic of the argument. I construct this retraction now over this base, and that implies that this thing is a trivial fibration, and therefore this map is a fibration. So that's our theorem. If you want to see the proofs of that retraction, the rest of it I think you've understood. I did that pretty slowly. If you want to see the construction of the retraction, look at my notes on GitHub. And let me mention that this proof itself is not entirely original. It's an analysis of a type theoretic proof that was originally given by Thierry Cocon and his co-authors in this paper on type theory, cubical type theory. The previous proof that I knew of the Frobenius condition for cubical and simplicial sets was due to Gambino and Zottler. It's a completely different approach. It's a much more difficult argument, I think. Of course, it's more general. It holds in other settings than this one. But I was very impressed to read Thierry's paper on type theory and see that he gave this quite simple type theoretic proof of this Frobenius condition using entirely constructive algebraic, what I'm calling algebraic reasoning. And that's what inspired me to rework that proof in this kind of algebraic categorical style. The proof that I've given you here is essentially a algebraic or categorical reworking of Thierry and Company's type theoretic proof. Okay, thanks very much. That's my contribution in honor of Eric.
So let's thank Steve. So there are some references in chat.
Oh, great.
Benno says that Frobenius is also proposition 14 in Gambino Garner's paper on the identity type refactorization system.
Okay, thanks. I missed that. Okay.
Yeah, and Nicola says that the polynomial functors also show up in Bisson-Joyal.
Oh, in earlier work of Joyal.
Yeah.
In the combinatoric stuff, or where is it?
Yeah.
It's a little boardism. Yeah, so it's a bit out there. Yeah, these are some short papers. Yeah.
Okay.
They're not as general as what Eric and Ike did.
Yeah. Not to take anything away from Eric and Ike.
I have a question.
Yes, please.
What doesn't work in simplicial sets?
You mean in this argument to prove the Frobenius condition? I think this argument could give the result for simplicial sets as well, but what you have to do is get the horn filling condition. It's not as simple to describe as this box filling condition. You have to use the fact that the boxes are retracts, or the horns are retracts of boxes. So there will be another additional step in there. But I think if you put that step in, you could use this argument in simplicial sets as well. I haven't been through the details of it, but I think that's the case.
Thanks.
The horns are not simply push-out products like this with an endpoint. They're retracts of such things.
Yeah, one needs to check that the two notions of vibrations agree.
Yeah.
But we know that. So then,
yeah, then it should work. Yeah. Thanks.
So Ivan has their hands raised.
Yes, I have one question. So in the case of partial functions, or say in a topos, but say in sets just to be simple, so the unit of the monad is you map X into X coproduct the point, yes?
Not coproduct, but paired with. Are you talking about the partial map classifier?
Yes, yes.
Yeah, it goes to the total sub-object. Take X goes to the partial map with the identity as the domain of the partiality. So it's a pairing in the sense of the sigma type.
Okay.
Maybe that's what you mean by coproduct. It's a pair, it's a sigma type pair with X and the identity as the domain of the partial map.
And in the case of spaces, so choose your favorite category of spaces where this is meaningful, what would be this construction instead on a concrete level?
At the moment, my favorite category of spaces is cubical sets. So
okay, let's stay old-fashioned.
And it would be exactly right. That's a little joke.
Okay.
But let's see.
Of course, for the case of cofibrations.
Yeah, I don't have an explicit description beyond the one I've given you. You can certainly define the polynomial endofunctor with the interval in spaces too. You can exponentiate by the unit interval. And so you can do this construction and you get a kind of partial map. Well, we don't have a subobject classifier though. So maybe you take the Sierpinski space as your partial map, and then you would have open subspaces. So you'd have partial maps with open domain. I guess you could use that as your partial map classifier for spaces. Sounds about right.
But shouldn't you classify cofibrations instead of subobjects? Because you don't really want to classify subobjects, you just want to classify cofibrations.
I'm not sure what you're asking for now. I thought you were asking for a partial map classifier in topological spaces. So one would be, you could use the Sierpinski space and make the partial map classifier for open partial maps. For all cofibrations, I don't know if that we have a cofibration classifier in classical topological spaces. We have one for simplicial sets. We can just use the subobject classifier in simplicial sets. That would be a cofibration classifier where the cofibrations are the arbitrary monos in simplicial sets.
Okay, this last part answered my question. Thank you.
Okay.
Torsten, you had your hand up for a moment. Did you want to say something or?
No, I think it was answered, but let me just emphasize this. I mean, you said that the proof by Gambino and Sattler is more complicated, but then it applies to simplicial sets as well. But now you're saying that you think you should be able to generalize used to simplicial sets as well. So that would be very interesting, I think.
Yeah, I agree. It would be interesting. However, the proof by Gambino and Sattler is also given in a kind of more abstract setting. And I don't doubt that it can also be, I mean, the examples they give are simplicial sets and cubical sets.
Yes.
But the proof itself is in the setting of presentable categories and accessible categories. And probably it can be applied in more general settings as well. We would have to ask Nicola that. But this algebraic proof at least works in the case of cubical sets, and possibly, probably in the case of simplicial sets as well. I like the fact that it also avoids the kind of infinitary reasoning necessary for the, I mean, it avoids all the co-limit kind of reasoning that you have to do if you're working in the locally presentable setting. So in that sense, it's more constructive or more algebraic. I think that I want to just make a comment about, related to the previous question too. I think that the connection between the synthetic domain theory and the notion of a dominance and the lifting monad on the one hand, and this kind of partiality point of view for the cofibrations and the weak factorization system is absolutely fascinating. And I think that can be explored more. It's also related to the theory of natural models that I have worked on, where we use it to give models of type theory. This dominance condition is a propositional case of the existence of sigma types in a natural model. So there's a complex of ideas there, including polynomial functors, synthetic domain theory, and partiality, which is a very rich kind of confluence of ideas that could be studied some more. I think Thierry is probably the one who has introduced this idea of partiality to capture cofibrations in his cubical type theory.
Yeah. Are there more questions?
I have one more slide. I'll just show it to you. It's how to get the retraction. It's not the whole retraction, it's just part of it. So that's a teaser for looking at the notes to see the construction. There are 4 steps because there are 4 maps in the retraction, and each one is a kind of elementary argument of this kind. Just to finish the verification that the proof is entirely algebraic as advertised. It's diagram chasing. The whole thing is this kind of diagram chasing using adjoints and push forwards and that sort of thing. In particular, it's quite stable, I think, this proof. So I'll put back the references. I'll provide the slides to whoever is collecting them.
I suppose that's Anders or Peter.
Okay.
Yeah. Okay, let's thank Steve again.
Thank you.